Welcome to the fabulous room 1065. I'm returned from my short leave of absence, and we're live.
In science, lesson 2, average speed and acceleration. In science 10, you learned that speed is distance traveled in a unit of time. You learn something like this. Now, we don't use S for speed. We use the letter V, partly because an S looks like a 5. Also, S is taken for seconds. We use the letter V. Why do we use the letter V? What else did we use for in terms of speed?
Velocity.
Okay, velocity equals distance over time. In fact, if you want to make it velocity, you added the vector symbol, and that's displacement over time. I am very sloppy. I get displacement and distance mixed up verbally. You'll often hear me call a displacement a distance. Sorry, I'm working on it even after 10 years of teaching physics. It's okay. As long as we get it right in our calculations, Rob, we're good. Average speed is total distance divided by total time. What we're talking about a lot this year is your instantaneous speed. It's the speed of an object at a particular instant, which may not be your average speed. In fact, it never is if you're accelerating. If you're accelerating because your speed's changing the whole time, your average speed may occur kind of halfway, right in the middle, but your instantaneous speed, it all depends. Some terminology. If an object moves along at the same speed over an extended period of time, we say that its speed is uniform or constant. What we're really saying is this. What did the letter A stand for last year? Acceleration. Boring. But we'll start out looking at it, and then we'll build from there. You spend like 3 weeks in Science 10 looking at uniform speed. Boring. Uniform speed is uncommon, but you can get nearly uniform speed in some situations. A car with cruise control tries to do a uniform speed, although if you actually look at the software, it slows down a tad, it speeds up a tad, it slows down a tad, it speeds up a tad, and it's sort of taking an average, but we'll call it a uniform speed. Fair enough. But usually a vehicle is making small changes in speed and direction all the time. If an object is not traveling in a straight line all the time, then its direction becomes important and must be specified. When both the magnitude and the direction of a speed are specified, we call these two properties, speed and direction, what did the V stand for? What did you say? Velocity. The velocity of an object. So you learned last year, if you say your car is moving at 80 kilometers an hour, that's a speed. If you say your car is traveling 80 kilometers an hour due north, you've given me a magnitude and a direction. That's a velocity. You called that a vector, by the way. We had vectors and scalars, and we'll get into that vocabulary too. The difference between speed and velocity becomes important when direction changes during a trip. And in particular, the one we'll flog to death quite a bit is this. Throwing something up and letting it come down. Because on the way up, we'll call that velocity most often positive. On the way down, we'll call that velocity most often negative. Although once in a while, because it'll be easier mathematically, let down be positive, we may do that. There's no rule that says down has to be negative. It's whatever's the easiest on your fingers and on your calculator, to be quite honest. Acceleration. Whenever the velocity of an object changes, the object experiences acceleration. In fact, acceleration is defined as follows. It's a change in velocity over a change in time. Now, how can your velocity change? 2 different ways. You can change the magnitude, or you can change the direction. So all of you have experienced acceleration in a car when they step on the brakes or when they step on the gas, because the magnitude of your velocity is changing. But I'm going to tell you right now, as I'm spinning this around my head, I'm going at about the same speed, but is the direction that those little weights are traveling changing? Let's see. If I freeze framed it right now, it's traveling towards Tawny. If I freeze frame it right here, it's traveling towards the front of the room, towards the board, yes? If I freeze frame it right here, it's traveling towards Ben, yes? And if I freeze frame it right here, it's traveling towards McKinley, yes? It is changing direction. If you've ever been on a merry-go-round, and someone is just keeping it going at a constant speed, even though your speed's not changing, you are still accelerating. Why? Because you're changing direction. Oh, and you feel it, by the way. That's why you have to hang on, because you're experiencing a force. We'll talk about that later. So acceleration is defined as a change in velocity over a change in time. Way too much writing. We have a lovely symbol for change in. Does anybody remember? You saw it last year. There is a symbol for change in. Atla. Triangle, we actually call it a delta because it's the Greek letter delta, even though it looks just like a triangle. So we would say this. Delta V over. Now, technically, I should write, don't write this down, delta T, but because it's impossible to do time without starting and stopping, without a change in, we've gotten lazy over the years, Trish, and we've long since stopped putting a delta in front of time. I think they still did in Science 10, and it drove me crazy. It's like, what would it be like? It would be like if you're writing a paragraph in your English class and starting every paragraph with the words, "This is written in English." It's self-obvious as soon as you see the word "the." Okay? It's the same. Time, you know, it's a delta. So we get lazy. Symbol for acceleration, who remembers from Science 10? Hello? A. Technically with a vector arrow, although sometimes we'll just be interested in the magnitude. Okay? Velocity has the same symbol as speed, which is V. Speed, V without the vector bar. Velocity, V with the vector bar. Now, if the velocity at the start of the time interval is V0, or sometimes we'll call it VI, the 0 is popular if you're British, but they won't say V0. Does anybody know how they say 0 in Britain? McKinley. Not. N-A-U-G-H-T. They'll say V naught. And I had a British physics high school teacher who was one of my heroes, and so you'll hear me slip into that once in a while. I'll say V naught or D naught or A naught. That's your initial, which brings us to this lovely little joke. Sorry for those of you at home. You missed my little comic. Okay. Generally, we call the starting velocity either V initial or V naught. I prefer to use V initial. What does it say on your formula sheet? V initial or V0? On your formula sheet, on your bright yellow formula sheet sitting in front of you. What did I use?
You use VI.
I use VI, okay. Oh, and if at the end, your final velocity, if we symbolize that with VF, then the change in velocity will be that, because change in anything is always final minus initial. Which gives us this equation here. Acceleration, that's change in velocity, that's change in time. I think this was the one that you were given in Science 10 last year. I always write it like this. This is what you can write down next to here, and I'm pretty sure this is what it'll say on your sheet. It probably says VF minus VI over T. Is that what it says on your formula sheet? It does, you just don't realize it. I rearranged it into a different form. We'll talk about that. Okay. Acceleration is defined as change in velocity, final minus initial, over change in time. We get lazy and don't write the change in for time because it's always a change in. Oh, note, change in anything is always final, takeaway, initial. That's going to be handy to have in your back pocket because there's going to be times this year, and definitely those of you that take Physics 12 next year, well, I'll say, hey, find the change in magnetic field. Hey, find the final magnetic field, find the initial magnetic field, and subtract them. Hey, find the change in voltage. Find the final voltage, find the initial voltage, and you know what you should do with those two numbers? Subtract them. Hey, find the change in momentum. Find the final momentum, find the initial momentum, and you know what you should do with those? Subtract them, okay? Worth having in your back pocket. Next page. Since velocity has two aspects to it, speed and direction, magnitude and direction, acceleration can occur if speed changes, that's what most of you are familiar with, or if the direction changes, that's what you saw when I spun those balls around my head, or both. We're going to mostly look at situation A. Okay? We're going to mostly look at situation A. All of you have built-in accelerometers. Your bodies can feel acceleration. But all of you, they work backwards. They work backwards. If you're ever in a situation and you ask yourself, I wonder which way I'm accelerating, Emma, what you really do is you ask yourself, which way do I feel like I'm accelerating? It's in the other direction.
What? Really?
Yeah. I'll convince you. Darian, ever been in a car? Okay. Ever been in a car where they had to hammer the brakes quite hard? Which way do you feel like your body is being thrown? I'm telling you, your car is accelerating, it's decelerating, it's slowing down. That's a backwards acceleration. Any of you ever been in a car that was at a red light and then someone really floored the gas like crazy? Okay, which way are you clearly accelerating? Forwards. Which way does your body feel like it's being backwards? Okay, let's take it one step further. How many of you been on the elevator before? Okay, when the elevator launches you upwards, which way does your stomach feel like it's staying or moving? Down. Which way are you clearly accelerating? Up. At the top, when it pushes you down, which way do you feel like your body is flying? Up. Which way are you clearly accelerating?
Down.
Okay, I'm not kidding. Your body has a built-in accelerometer. You just need to realize that it's backwards. It's backwards. How many of you have been on the Music Express ride at the P&E, the one that goes in a circle really fast? Okay,
Yeah.
you ready? You ready? You ready?
Mm-hmm.
Which way do you feel like you're being pushed on that ride? Which way? Give it to me in terms of towards the center or away from the center.
Away from the center.
Which way are you accelerating then?
Into the center.
I'm telling you, you are. This is people. A lot of people, when they move in a circle, they think, I'm accelerating outwards. You're not. I guarantee you're not. You're accelerating inwards. We'll talk about circular motion, which is weird in Physics 12. But even as something as simple as, let me give you an example. I got to pause the video for this one. Example 1. A runner racing in a 100-meter dash accelerates from rest to a speed of 9 meters per second in 4.5 seconds. What was his average acceleration during this time interval? I'm going to be showing you a method or an approach that I call DFIC. You're going to learn 2 acronyms from me this year. One is DFIC and one is DULP. And you're going to hear me say, when in doubt, DFIC and DULP. Okay? And what does DFIC stand for? DFIC, it's an acronym, and it stands for list your data, find a formula that has everything of your data and what you're looking for in it, insert the numbers, and then calculate the answer. Eventually, Curtis, you'll get good enough where you can skip some of this, but in our notes always, so that when you're studying you know what the heck we did, and when in doubt, always DFIC. So we're going to start out listing your data. First thing I always ask is, what are they asking me to find? Darian, what are they asking me to find? What symbol am I using for acceleration? I'm going to go like this. A equals question mark. I feel better. My question's no longer blank. I'm more relaxed. Then I look through the entire question, looking for numbers or words that tell me information. The first number that I see is 100. What is that 100? What are the units next to that 100? Meters. You know what? That 100 is a distance or a displacement. I'll call that a d. Now, there is a phrase that you always want to notice here in physics. We're going to underline it. It's this phrase right here, from rest. That tells me something. What does that tell me? Initial velocity is 0. And then I see a 9. What's that 9? What are the units right next to it? Hey, what's that? It's a velocity, which has got to be final velocity. And then I see a 4.5. What's that 4.5? I'm looking for an equation that has, Rob, an a in it for sure. And then it has these other ones. Now, eventually you'll have about 10 or 15 to choose from. Right now, you only got one, because the only equation I've given you is this one here, acceleration equals. So, Rob, stay on your page, but double check with me. Did they want me to find A? Say yes. Did they give me V final? Look in front of you, look in front of you. Were you with me writing this down, I hope? I didn't catch you zoning out, did I?
I didn't write down the D100.
Okay. Did they give me V final?
Yeah.
Did they give you V initial? Did they give you time? So I can solve. And you know what, Rob? Brilliant. Actually, that distance equals 100. I don't need it. It was extra info. Fine. So the formula, the equation is A equals V final minus V initial over T. Tawny, is there more than one letter on the top?
Yeah.
Would that suggest I better put the top in brackets?
Yeah.
Oh, just saying. Let's see here. So, data, F formula, insert. V final, 9 minus V initial, 0, all over 4.5. What's the average acceleration? I don't think I need a calculator for this, because what's 9 take away 0? 9 divided by 4.5? By the way, you'll find out this year, if a question works out evenly, like this one, Mr. Kamosi made it up, because he's very good at mental math compared to me. If a question doesn't work out evenly, the odds are I made that one up because I didn't care enough to bother trying to crunch the numbers ahead of time and see if they would work. So, in case you ever wonder, if a test question works out evenly, my neighbor made that one up. If it doesn't work out evenly, it's on me. You get 2. By the way, how many sig figs? How many sig figs right here? 2. How many sig figs?
2.
We're dividing. How many sig figs technically should there be in my answer then? And I've told you I'm not going to take marks off for sig figs for the remainder of the year, but I'll enforce it. And the units for acceleration are meters per second squared. Also, you'll notice all I can find is the magnitude. I didn't bother putting a vector sign on the A because, Curtis, they haven't given me any kind of a direction in here. That's fine. So, the standard unit for expressing acceleration is meters per second squared. If you have an object that's accelerating at 1 meter per second squared, that means every second its speed is increasing by 1 meter per second. So let's suppose, well, let's try a few more. Example 2. A UFO is reported as accelerating from rest, I'm going to underline that, to 680 kilometers per hour in a time of 2 seconds. Okay. Kai, what's this question asking me to find?
The acceleration.
I'm going to write A equals question mark. And then I'm going to go read through really quickly, looking for physics words or numbers, and I'll look at the units to figure out what's what.
Yeah.
What's that from rest?
It means the initial is 0.
Nice. Okay. By the way, from rest almost always means V initial is 0. Comes to a stop means which one is 0?
The final.
V final. And that we'll also look at that because that's a good physics situation too. Kai, what's that 680?
Your final velocity.
What's that 2?
The time.
Who can see what's yucky? What's icky about this question? Okay, the units. I don't do math. Now, cars are measured in kilometers per hour, so we did a whole unit on unit conversion, and I'll tell you why, Kyle. Primarily for this single conversion here. The most common one you're going to do is going from kilometers per hour to meters per second, because cars and airplanes and fun stuff are often measured in kilometers per hour. So we need to do a conversion. I need to go from kilometers per hour to meters per second. The first thing that I would normally do, Rob, is I would write down what they gave me. I think I already did next to VF. Yes? Okay. Well, Emma, do you want to get rid of kilometers first or hours first? Doesn't matter. Pick. You want to get rid of hours first? Okay, so I'm going to multiply. Where is hours right now, on the top or on the bottom? Where is it going to be in my next fraction then? Do you by chance know how many seconds there are in 1 hour? Have you spotted that little shortcut? Because we've done it a few times, but if you haven't, do you know or not? So what can you go from hours to what? Sure. And you're saying 1 hour is 60 minutes? You would be correct. Now we're in kilometers per minute. Where is minutes right now in my second fraction? Where is it going to be in my next fraction? And I think it's 1 minute is 60 seconds. Is that yes, 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 yes? Okay, that gets us to kilometers per second. Now I got to deal with kilometers. Curtis, where is kilometers in my original fraction, top or bottom? So where am I going to put it in my next fraction? Did you say on the bottom? You'd be right. By the way, here was by far the most common mistake in this section on the test. Look up, look up, look up. Kids did this. This is wrong. Now, why is that wrong? Here's what I'm saying. According to your formula sheet, you can replace a K right here with a 10 to the third. That's what we're saying. That's how you know where that 10 to the third goes. You're saying on the bottom, instead of writing a 10 to the third, I just put a K because that's what K means. But on the top, in front of wherever there was no prefix, I put the actual number. That was by far the most common mistake. Psst. Put your pencils down. Can you see, Kyle, what I'm going to do to that 680? Times it by what and divide it by what? And? I think I'm going to do this then, if I hear you correctly. It's going to be times by 1,000 and divided by, I think 60 times 60 is 3,600. Yeah. That's the same as, that's the same as, I think, just dividing by 3.6. Times by 1,000 divided by 3,600. So you ready? Over here in the margin. Pick your pencils up. To go from kilometers per hour to meters per second, divide by 3.6. Now 3.6 isn't too bad a number to have to remember, because you may have noticed there's a 60 times a 60, which is 3,600, like maybe the 3.6. The real question is that kids forget is, do a divide or multiply. I'll teach you a dumb, easy way to figure that out as well. I don't actually have memorized divide by 3.6. I just know the conversion factor is a 3.6. Anyways, what is 680 divided by 3.6 in meters per second, please? You got 188.8888888? No? Try again. 680 divided by 3.6, or 680 times 1,000 divided by 60 divided by 60. I'm going to write down 189. I'm going to keep this on my calculator, though. Let's come back. Oh, I've forgotten who I started this question with. I think it was Kai. Was it Kai? Yes, it was.
Yeah.
What are they asking me to find?
The acceleration.
Which is good, because I wrote, okay. So I'm looking for an equation right now, Kai, that has acceleration, initial velocity, final velocity, and time. And right now you only got one, but I'm going to start this questioning process so that in about 5 lessons, when you have 5, this is the process checklist you'll go through. Is that okay, Dane?
Yes.
So acceleration is going to be
A equals.
V final minus V initial. Is that what you're going to say to me?
Yep.
And by the way, you can say final velocity, or you can just go VF minus VI over T, which is less verbalizing and easier to write down. Talk to me.
So that would be 188.
So I'm going to write 189, but I'm going to use my answer button on my calculator. Have I yelled at you about getting a good calculator yet? Yep. Minus 0 divided by answer minus, I guess I didn't really need to type the minus 0 because minus 0 doesn't change anything. Divided by, with 2 seconds?
Yep.
94.4. Let's see. How many sig figs here? 2. How many sig figs here? Okay, fine. 94 even. Yep.
I got 94.5.
But I'm willing to bet you didn't use the answer button. I'm willing to bet you used 188.9 or 189. I used this. I'd take yours. What I'm saying is, if you can be accurate and store a number on your calculator without rounding off, always try and avoid rounding off in the middle of your calculations.
All right.
We round off at the end.
All right.
If we have to round off in the middle, I usually carry 4 or 5 sig figs. I'll carry 2 or 3 extra decimal places
Okay.
because I don't want to use inaccuracy to find more inaccuracy. Okay. By the way, I wrote down here, the speed of the UFO is increasing at 340 kilometers each second. This acceleration might be written as 3.4 times 10 to the second kilometers per hour per second. I've second-guessed myself on this about 10 times, Zach. I hate this. So we did our conversion first, so you can scribble that out. We're not going to use kilometers per hour per second as a measure of acceleration. I think it's yucky. It's like fingernails on the blackboard as far as I'm concerned. Okay? So what can you try? You'll get lots of time to finish this. By the way, if you have any other NHIs, because you got your email yesterday, you want to make sure you get those in. I will do a re-update probably Tuesday or so, but for now. Number 1. Problem. I gave the answer in kilometers per hour per second. Give me 1 second here. Where's my calculator? Oh, I got to use this cheap, ugly one. Where's my silver? There's my silver calculator. It's going to be 60 divided by 3.6 equals divided by 3 equals. Ideally, you're going to get 5.56 meters per second squared, I think, in number 1. Okay? So it says, give your answer in kilometers per hour per second. No, I don't like that unit anymore. Number 2, don't give your answer in kilometers per hour per second. Give me a second here. It's going to be bracket. You should get an answer of 0.56 meters per second squared. Wow, I included a bunch of these. This was dumb. Scribble that out. Scribble this out. Convert it to meters per second. So it's going to be 20 divided by 3.6, close bracket, divided by 4. I'm doing these in a big hurry. Oh, there is the acceleration in meters per second squared right there. There you go. I did that already. Well, that was clever of me. Usain Bolt, I'm good with that. Woodpecker, I'm good with that. And then number 6 is trying to give you some context. How many of you have heard the term G-force before? How many know what it means? What's it mean? Gravity. Okay, you're on the right track. First of all, technically, it's not a force, it's an acceleration. It's misnamed. So when they talk about G-forces, what they really mean are G accelerations. And 1 G is that big, 9.8 meters per second squared. By the way, really close to a nice round number of 10. It's really close to 10. And in fact, when I'm at Playland, standing in line and trying to actually calculate, and yes, I do actually try and calculate, I use 10 to do the math in my head. It's a nice number. So 1 G, about 10, 9.8. 2 Gs means you're experiencing about 20 meters per second squared. 3 Gs, you're experiencing about 30 meters per second squared. For human beings, 8 and 9 is survivable with broken bones. Basically, well, 9 Gs, if you're undergoing 9 Gs, that's exactly the same as 9 people dogpiling on top of you. Okay? That weigh exactly the same as you. You weigh 9 times your weight at that moment. There have been instances, in fact, later on, we'll calculate, as far as we know, the person who has survived the biggest G-force, it was a race car driver and survived. But anything in the, if you watch Mythbusters, anything in the 20 G range is usually considered concussion terminal. Anything in the 50 or higher G range is usually considered you'll turn into a pancake terminal. Anything above that is bleh. Okay? So what number 6 is asking is, from number 5, where you're calculating the acceleration that woodpeckers go through, you'll find the number of G-forces, even though it's not a force, the number of Gs they experience is crazy. And as a matter of fact, they're looking at woodpeckers to redesign and redevelop helmet technology because, wow, nature has got some really good engineering if a woodpecker's brain can handle that kind of impact and not have a concussion every single time they hit the tree. They don't. So you can also try number 6. How many have been on the elevator before? Okay. On the way up, you typically experience about 3 Gs. So that feeling where you feel heavier, you're about 3 times your body weight. As far as I know, and I haven't been to play, as far as I know, the Scrambler is the ride that has the biggest G-forces. Do you remember, who knows what the Scrambler is, right? Okay. That's the one where you really feel like you're getting pushed outwards. By the way, if you feel like you're getting pushed outwards, which way are you really accelerating?
Inwards.
Okay, and you're accelerating inwards at about 4.5 Gs. At that, there's always that not too bad, not too bad. Oh, right now, really hard. Good, good, good. Not too bad, not too bad. Oh, right now, really hard. That moment right there, you're peaking at around 4. Laterally, sideways, we can handle a lot more. It's vertically that's much tougher because your lungs and your heart don't like that. But laterally, I can, if Dane goes against the wall and he leans against the wall and I push against, as long as I don't impact him, and I just start pushing hard against your shoulder, and then Ben starts pushing hard against my shoulder, and Kai starts pushing hard against my, you could probably handle 7 or 8 people before you'd be saying this is a little awkward and uncomfortable. So sideways, we can handle way more Gs. Anyways, your homework is 1, 2, 3, 4, 5, and 6. On a Shaq, on a separate piece of paper, please. If you're looking for a heading, you can call it Lesson 2, average speed and acceleration. You got 15 minutes, 6 questions, lots of time.